Good morning all. Myself Mamta. Today I am going to discuss the topic thermodynamics in that heat engine, that is Carnot's heat engine. Now let us see what is heat engine. Heat engine is a device by means of which heat can be continuously transferred into useful work. So actually heat engine absorbs heat and some amount of heat will be converted into work. So here Carnot's heat engine. So Carnot's heat engine is an ideal heat engine. So we cannot realize or imaginary this Carnot's heat engine in practice. So that is, it is an imaginary ideal heat engine. It is free from friction and other imperfections of actual heat engine, and its efficiency is maximum. So that is 100%. So now let us see, so what are the components of Carnot's heat engine? Carnot's heat engine consists of a cylinder having perfectly non-conducting walls and a perfectly conducting bottom in which a perfect gas is enclosed. So here the working substance in Carnot's heat engine is a perfect gas. Next, a hot body of infinite thermal capacity. A hot body, also called as source, and it is maintained at higher temperature. Any amount of extraction of heat from the source does not change its temperature. That is, it having infinite thermal capacity. Third part, a cold body of infinite thermal capacity. A cold body is also called sink, which is maintained at lower temperature and having infinite thermal capacity. Fourth is the perfectly non-conducting platform, which serves as the stand for the cylinder. So that is perfectly non-conducting stand. This working substance in Carnot engine is taken through a reversible cycle consisting of 4 stages, and this is represented on a PV diagram. So this cycle is called as Carnot's cycle. So now let us consider, let the working substance be at the initial state having coordinates P1, V1 and T1. So that is, let P1, V1 and T1 be the initial pressure, volume and temperature of the gas respectively, and it is represented by the point A on the PV diagram. So this is the PV diagram where volume is taken along x-axis and pressure is taken along y-axis. The state A represents the initial state of the working substance with the coordinates P1, V1 and T1. Now let us consider the 4 stages of Carnot cycle. So first stage, isothermal expansion. For isothermal expansion, the cylinder is placed on the source and let the gas expand slowly. Since we are expanding, the piston is moved outward. Since the piston moves outward, volume increases, resulting in the fall of temperature. Since it is isothermal process, temperature has to be kept constant. So therefore, as the gas is in contact with the source, heat is absorbed from the source, and this maintains temperature constant. This isothermal expansion is represented by the curve AB. Let Q1 be the amount of heat absorbed by the gas from the source. So then the work done in expansion of the gas from the pressure from P1 to P2 and volume from V1 to V2 is given by W1 equals Q1 equals integration of V1 to V2 PDV equals RT1 log V2 divided by V1, and this will be equal to area under ABGE as indicated in the PV diagram. Second stage is the adiabatic expansion. For adiabatic expansion, the cylinder is placed on the non-conducting stand, and now allow the gas to expand adiabatically. Since we are expanding, the piston is moved upward so that its temperature decreases. Let the decreased temperature be T2. This is represented by the curve BC. Then the work done by the gas in the expansion from P2 to P3 and volume from V2 to V3 is given by W2 equals integrating from V2 to V3 PDV equals R divided by gamma minus 1 into T1 minus T2. So that it will be equal to area under BCHG as indicated in the PV diagram. So next, isothermal compression. So now the cylinder is placed on the sink. The piston is allowed to move inward so that the gas is compressed. In this process, the temperature of the gas tends to increase and maintain constant by rejecting heat to the sink. Since it is an isothermal process, temperature has to be maintained constant. So the increase in temperature is rejected to the sink. Let Q2 be the quantity of heat given to the sink. This change is represented by the curve CD. The work done during the isothermal compression from pressure from P3 to P4 and the volume from V3 to V4 is given by Q2 equals W3 equals integrating from V3 to V4 PDV equals RT2 log V4 by V3, that will be equal to area CHFD. And next, the last stage or the fourth stage is the adiabatic compression. For adiabatic compression, again the cylinder is placed on the non-conducting stand and the piston is allowed to move further downwards so that the gas is compressed adiabatically till the temperature becomes T1 or the gas attains its initial state. This is represented by the curve dA. The work done on the gas such that the pressure changes from P4 to P1 and the volume from V4 to V1 is given by W4 equals integrating from V4 to V1 PDV equals R divided by gamma minus 1 T1 minus T2, and this will be equal to area DFEA. So now the net work done by the gas is given by total work done W equals W1 plus W2 minus W3 minus W4. So that will be equal to area ABCD as indicated in the PV diagram. Since here W2 equals W4, so the total work done or the net work done W will be equal to W1 minus W3. But we have the net work done will be equal to net amount of heat absorbed. Amount of heat absorbed will be equal to Q1 minus Q2. So therefore we have Q1 minus Q2 equals W1 minus W3. But according to the definition of efficiency of the heat engine is given by, that is eta equals heat converted into work divided by heat absorbed from the source. So heat converted into work is given by W divided by amount of heat absorbed, that is Q1. So that will be equal to Q1 minus Q2 divided by Q1. So simplifying, this will be equal to 1 minus Q2 divided by Q1. So but we have Q2 by Q1 will be equal to W1 by W3. So now substituting for W1 and W3, we have RT1 log V2 by V1 and RT2 log V4 divided by V3. R gets cancelled. Finally we have T1 log V2 by V1 and T2 log V4 by V3. So now from PV diagram, the points P and B and C lie on the same adiabatic. So therefore the relation between temperature and volume in case of adiabatic process is given by Tv to the power of gamma minus 1 is equal to constant. So by using that expression we can write T1 V2 to the power of gamma minus 1 equals T2 V3 to the power of gamma minus 1, or simplifying we have T2 by T1 will be equal to V2 by V3 whole to the power of gamma minus 1. Similarly, the points D and A lie on the same adiabatic. So thus we have T2 by T1 will be equal to V1 by V4 whole to the power of gamma minus 1. So now comparing equations 7 and 8. So comparing the above two equations, we can write T2 by T1 will be equal to V1 by V4 whole to the power of gamma minus 1 will be equal to V2 by V3 whole to the power of gamma minus 1, or V2 by V1 will be equal to V3 by V4. Substituting this in equation 6, we get Q1 by Q2 will be equal to T1 by T2. So therefore, expression for efficiency eta will be equal to eta equals 1 minus T2 by T1 or 1 minus T2 divided by T1. So this is the expression for efficiency in case of Carnot's heat engine. Thank you.